Okay, hi everyone. This is the third video of the 13th week when we will discuss exercises that were intended for labs this week. And we will deal with network sampling that we have also discussed in the last lecture. So let us together read the handout for the exercises. So you're given 4 large networks in standard formats, and these are the, some internet map, a sample of Facebook, an email communication network from the Enron company, and a part of the Google Web Graph. Later on, we will be studying also 2 Facebook networks, but let's leave that for later. So the first exercise reads that try to implement a simple random walk sampling and apply it to the largest connected components of the 4 large networks above until you sample 50% of the nodes with repetition. So you can sample the nodes multiple times. And for that you can use the same routine that you have used in homework 2 or homework 3, if I'm not mistaken. And if you remember from labs, we know that if we do some random walk exploration on the network, the probability that we will find a particular node, that we will encounter a particular node, is proportional to its degree. So if we would now want to get an estimate of some properties of the nodes in that network, we can simply measure those properties, but then when we are computing the expected value or the average, we can correct for this sampling bias that we are more likely to encounter high degree nodes than low degree nodes. And in our particular example, we will try to estimate the average degree in the network, which is the simplest maybe property that you could estimate. So imagine that you sample S nodes. This small s should be 50% of all the nodes in the network. And we get the degree sequence of these sampled nodes, which is basically a list of their degrees. And since I can sample with repetitions, some nodes will appear multiple times, their degrees will appear multiple times in that sequence. And then if I would simply estimate the average degree of the complete network using the average value of these degrees that I have sampled, I could use this simple formula, but this will give me a biased average because I'm more likely to encounter high degree nodes. And we can correct for that, as we have seen in the lectures, and the corrected estimate would look like this. So I take the size of the sample divided by the sum of the reciprocal values of the degrees. And as I also mentioned in labs, look at these 2 formulas. The first one is a classical formula for average, whereas the second one seems completely wrong. It seems that I have no idea how to compute the average, but as we will see, this estimate will actually correct for the biases that we get from random walk and will give us a much better estimate of the average degree. So we will apply this procedure to all these 4 networks above, compute their biased average and also the corrected average, and see how close we are to the true value that we can also easily compute. The code for that is online, but it's simply just a random walk when you sample the nodes, so we're not going to look at that. Let us just look at the results. So the log file is of course also available online. So our first network is an internet map with 75,000 nodes, and we sample 50% of the nodes. And the correct average degree, as you can also see above, is 9.4. If we do this random walk sampling and just take the average of the degrees that we found, the value that I got here is around 1500. So it's much higher than the actual average. And this is expected because we are more likely to encounter high degree nodes. They appear more frequently in the average, and if I am not correcting for that, I will get a much higher value than the true value. However, if I correct for the sampling biases using this that weird formula that you can see in the handout, notice that I get a very close approximation of the average degree. In contrast to before, this is like the biased estimates is like 3 orders of magnitude larger than what I should get, whereas the corrected estimate is very close to the true value. And you could use the same procedure if you know that if you're sampling with random walks to estimate any other property, not just the average degree, but maybe also some external properties. If this would be a social network, you could maybe try to estimate what is the proportion of gender, or the average age of people, or their average monthly income, or anything like that. In any of these cases, when you take the average, don't just take the regular average, but correct for the biases, and you will get a much better estimate of the true value. And if I go on, you will see that I get similar results in all 3 networks that we're dealing with. Next is a social network with an average degree of 26. My estimate is around 28, whereas the uncorrected estimate is around 90, again, much higher. The difference is not that astonishing in this particular case, apparently mostly due to the fact that the highest degree nodes are not that, the highest degrees are not that large in this particular network. If we go to the email communication network, again, the correct average is 7.01. The corrected estimate is 7.07, again something very close, whereas a biased estimate is again 172, again much larger. And I expect similar result for the Google Web Graph. The average degree is 10. My corrected estimate gives me 9.7, whereas uncorrected estimate gives me 175 roughly. So once again, a much higher value. Of course, since I'm just sampling, my corrected estimate is not exactly the same as the true value. However, it comes very close. So what we have learned is that at least in the case of random walk sampling, we know what is the probability of encountering a node is proportional to its degree. And when we do some estimates based on that sample, we can easily correct for that. Well, of course, it's also important that you sample at least some reasonable part of the network. Imagine that I would sample maybe just 1% of the nodes or so on. The results will not be that clear, because in that case it will largely depend on where do I start, what is my initial random node, where I start my random walk. How to correct for that, at least to some extent. Usually people would not do just one random walk, but do multiple random walks if you cannot do very large random walks, in order to sample different parts of the network and get a better average. So this is it regarding this first exercise. And I should also highlight that this, as you have seen also in lectures, this random walk approach is one of the few cases in network sampling when we know how to correct for the biases. In practice, for most other approaches, we either do not know how biased we are on in which direction, or we know that, but we are unable to correct for that, like for instance with snowball sampling, where the probability of encountering a node is proportional to the eigenvector centrality. And to compute the eigenvector centrality, we need the entire network, but if we would have an entire network, we can work with that, and we don't need any sampling, so things break down. Okay. Let us also move to the second exercise, when we are given two very large samples of Facebook that were collected by I think that from Emilio Ferrara, who collected these samples of Facebook more than 10 years ago, when Facebook was still to some extent a bit open. And both of the networks have several millions of nodes and links, so these are really large networks, although still compared to the entire size of Facebook, these are just some tiny fractions of Facebook. As it was published by Emilio, we know that these two samples were obtained with two different techniques. One was the classical snowball sampling, that you know it's kind of like a breadth first search, and he did a snowball sampling from different parts of a network, collected all these samples, and then merged them together into one network. The second network was collected by some node selection techniques. When you select the nodes from a network, that it's called rejection sampling. This is no longer possible to be done nowadays, but like 10 years ago, all Facebook users had a unique ID, and knowing their ID, you can construct the web address to get to the profile of that particular user. And those IDs were in a particular range, say from 1 to, I say 10 million. And each of us was given a random ID from that range. So how did the sampling proceed then? Is that you generate a random number out of this range and check whether that user exists. And if it does, you collect its information, its neighbors, and so on. Whereas that user does not yet exist, there is no user with that ID, you reject that part of that particular sample, that particular node, and this is where the term rejection sampling comes from. So, and again, this was done over multiple waves of the sampling. Now that you know how both of these two samples of Facebook were sampled, the question is, can we, looking just at the structure of the samples, figure out which of the networks was sampled with one of these two techniques? Okay, so you are given two large samples of Facebook, and these are only available in edge list format because the files are super large. So if we together read the exercises, the samples were generated by rejection sampling and snowball sampling, and your task is to try to figure out from the structural properties of the sample which network is which sample is which. And as I said, that these are still very tiny samples of Facebook, so the results might not be obvious from the structure. I have computed some of the properties of both of these two samples. You can see here the number of nodes, and in both cases the number of links. In both cases we have one large connected component and many other components, and then you can also see an estimate of the power law exponent, Newman's assortativity coefficient, their average clustering coefficient, modularity, and so on. So, and looking at these values, it does not seem entirely obvious which sample is which. And your task is that something that you can work on at home is to try to compute some structural properties of these samples that will clearly distinguish between rejection sampling and snowball sampling. Not just looking at, let's say, the size of the largest connected component or something. And this is, of course, not a trivial task here because networks are super large. And as I said, that based on the results that I'm giving you, I don't think that it's entirely clear which network is which. I can tell you that the Facebook 1 was obtained with snowball sampling and Facebook 2 was obtained with rejection sampling. So if you have time, try to figure out some simple structural property of these networks that will clearly distinguish between these two networks. And if you found something very interesting, please post that on Piazza so that other people can see it as well, and you will get some extra credit for that. Okay, that is it regarding these labs and regarding the sampling. So if you have any questions, please post them on Piazza. Please also post solutions to the second exercise to Piazza if you get some. And that is basically it. So thank you for listening and see you in the next video.